All right, welcome back, everyone. Welcome to day 3 of the Great Lakes Security Conference. And today with us, we have Branden Clark, a senior security researcher over at Lockheed Martin, and he'll be talking about Windows driver security. And with that, I'll pass it over to him.
Hey everyone, am I coming through okay?
What was that?
Am I coming through okay?
Yeah, loud and clear.
Perfect. All right, let me share slide deck real quick. All right. Chat window. Cool. All right, yeah, so I'm going to be talking about Windows driver security, more specifically from kind of like an attacker's point of view that might be interested in taking advantage of kernel access on the system. So real quick about me, since I graduated, I've been working at Lockheed Martin ATL in Northern Virginia. We also have an office in Cherry Hill, New Jersey. In school, I was a member of the computer security club there called RPISec. So jumping right in, for attackers, kernel access is desirable for a bunch of reasons. It allows you to do things that you can't do from user space. It's a whole new privilege level. One of those things is that you can intercept file or network operations, and that allows you to do good things. Antivirus providers do this to protect their own files. They'll intercept file operations, and if they see that you're trying to edit one of the antivirus's files, then they can block you from doing that. But you can also use that to hide things from user space or hide things from antivirus. It's kind of this same back and forth kind of rabbit hole of somebody makes cheats, somebody makes anti-cheats, somebody makes anti-cheats. And kernel access really gives you a lot more power to do both of those things because there's a lot less introspection, both from user space and also within kernel space itself. So really the only two ways of gaining kernel code execution on Windows is either legitimately by loading a driver or through an exploit, either an exploit of a bug that's in the Windows kernel itself or through a driver that's running in the Windows kernel. So Microsoft, as far as like bug bounties and security servicing criteria goes, doesn't consider administrator to kernel starting as a administrator on the system and then getting kernel code execution as a security boundary. So if you find any flaws, they're most likely still going to fix them, but they're not going to like award a CVE or a bug bounty or anything. That said, they still want to keep the kernel kind of this trusted space, partly because the code is running in there. If there's a problem with it, when it crashes, it doesn't just bring down one process, it brings down the whole system. You get a big blue screen of death and your whole system has to reboot, which is bad for Microsoft from like a public eye point of view, because when most people get a blue screen, they go, hey, that's Microsoft or Windows's fault. They don't attribute it to the Intel storage driver or something specifically. So it looks bad rep on Microsoft. But also from a security standpoint, because like I mentioned in the previous slide, it gives you a lot more power. So despite it not being a boundary, Microsoft has taken steps to prevent administrators from loading arbitrary code into the kernel. You do need administrative privileges to load drivers, but starting in Windows Vista, they introduced driver signature enforcement, or DSC, which prevents loading of kernel drivers that don't have trusted, valid digital signatures. So here, and you can go and look at the certificate or in signature of a driver on your system by right-clicking it and choosing properties. And there's a little digital signatures tab at the top there. And this looks like it's the VirtualBox driver. You can see it's signed by Innotech. Windows even tells you the digital signature is okay, meaning that they verified the signature against the file itself to make sure that it hasn't been tampered with. And then you can also see the full certification path, starting with the signer Innotech and then going all the way back to a global root CA. So without having this full chain of trust all the way back to a root CA that's trusted by your system, and also without making sure that the file itself hasn't been tampered with, Windows will just refuse to load your driver. And that's been really the only thing implemented by Microsoft for quite a while to keep arbitrary code from getting loaded into the kernel by an administrator. Up until Windows 10, they modified it a little bit. It is called attestation signing, and it's only enforced on drivers that are signed after July 28, 2015 in order to maintain backwards compatibility with drivers that were developed and signed prior to that date. And the change that this adds is that rather than that VirtualBox driver that was signed by the developer itself, now Microsoft requires that drivers be submitted to Microsoft directly for both testing by Microsoft and signing by Microsoft. So here's a snippet from MSDN outlining the process. Not only do you have to acquire a code signing certificate now, but you also have to create a installer package, submit it to Microsoft, wait for them to validate it and test it against a big list of requirements that they have. And then they will give you a download link to download the signed driver package. And here's an example of a Symantec driver. And as you can see, it's signed by Symantec, but it's also signed by Microsoft. And on the certification path, it goes all the way back to a Microsoft root trust authority. And so that is the new requirement for drivers. And that's a much bigger requirement. Now you can no longer just spend some money to get a root CA to sign your code signing cert and then load whatever code into the kernel you want. Now you actually have to upload it to Microsoft, which from an attacker standpoint is going to expose you, give you risk. You're not going to want to just give your code straight to Microsoft. And in addition, you have to go through this whole other validation process at Microsoft as well. So obviously that process is long and expensive, and Microsoft can't expect regular developers like antivirus vendors or even like the people that develop the Wireshark driver to go through that whole process every time they want to test or debug their code. So they've provided ways to disable driver signature enforcement for testing and development environments. One of them is to enable test signing mode, which you can do with this bcd edit command line that adds an option to the boot. It adds a boot option. And then the other one is in Windows 8 and Windows 10. You can go into the special startup menu or boot screen, and there's an option here to disable driver signature enforcement. And with this disabled, it will allow you to load your test driver without it being signed, or in test signing mode, it needs to be signed by a test signing certificate, which is just an option you can choose in Visual Studio while you're developing. However, from an attacker's standpoint, you're not really going to want or even be able to do either of those things in the wild. Both of those options require either a reboot, physical access to the machine, or both. And in the case of the test signing mode option, it even leaves a watermark in the bottom right-hand corner of the screen saying that test mode is enabled. And that's a big indicator or red flag too. So that's not really something that you want to do in an offensive scenario. So for more technical details on driver signature enforcement, I highly recommend checking out this blog post by Juru. It has a lot of great detail, some of which we're going to go into in the next following slides. So the question is, if turning off driver signature enforcement allows you to load arbitrary code into the kernel, how do you do that offensively or without causing a reboot to the machine? So the first step in answering questions like this is usually to figure out how it is implemented by the system or how it's used properly. So we saw that there are two options for actually turning it off the right way. So what do those do kind of behind the scenes or under the hood to make it so you can load arbitrary code into the kernel? So there is a DLL called CI for code integrity DLL, and it has a whole slew of exports for allowing Windows and other vendors to work with code signing and integrity. There's an initialize function. There's a function for it to check signed file, validate file object, get PE or portable executable information. So all sorts of stuff that the kernel might be using to actually validate the driver when you want to load it. So going into NTOS kernel, the Windows kernel itself, and doing some cross references against those exports, try and find where they might be used or how they might be used by the kernel, we come across this function sep initialize code integrity. At the top of this function, we can see that it initializes this options variable to 6, and then somewhere in the middle of the function, it might change that value with whatever is at RDX. And then eventually, right before it returns, it passes it to the CI initialize export that we saw before as the first argument. So we saw in that code that the default value for the code integrity options on the system seems to be 6. So if we attach WinDebug as a kernel debugger, we can dump the value of that options variable and actually see that it is 6 on a normal system. So what happens to this options variable if we enable test signing? It flips the 8th bit and leaves the 2nd and 4th bits alone that were there for when DSC is enabled. So if we disable DSC from the startup screen, you can see it leaves the test signing bit flipped, but turns off the other 2 bits that were set previously. And then now finally disabling test signing mode and driver signature enforcement from the startup screen with BCD edit leaves the options value all 0s. So that kind of begs the question, is all we have to do to turn off kind of this mitigation called driver signature enforcement is set that value to 0? So let's try it. So real quick, starting from a completely normal system, make a silly driver called moo. And the normal way of starting a new kernel driver in Windows is to create a service of type kernel and then start it. And you can see here that when we try to do that on a normal system, it says Windows cannot verify the signature for this file. So it's rejecting our driver because I just made it in Visual Studio real quick. It's not signed, doesn't even have a test signature, nothing like that. Windows doesn't want that code running in the kernel. So what happens if we were to modify that code integrity options flag at runtime, which we can do with the kernel debugger with a real quick command. And we're just going to set it to 0, which is the option that we saw when we had disabled driver signature enforcement, the right way for testing and development environments. And now when we go to start our driver, it actually runs it. It's running in the kernel. We now have kernel code execution. However, we're back to kind of like the same point we were before, where we can't use a kernel debugger in a defensive scenario either. And we know that since we needed a kernel debugger to set this flag, that the options variable is in kernel space. So if you need kernel code execution to set this flag, and you need to set this flag to get kernel code execution, it starts to look kind of like a chicken and egg problem, or like kind of a circular logic problem. But actually it's not. And the reason is because of Windows, or people who write drivers and then get those drivers signed. For example, here is a CVE from 2007 and a speed fan driver, lets you gain privileges and load unsigned drivers. There's another one here for some drive crypto. There's another one for cpuz, arbitrary memory write. This one was pretty bad and got a lot of attention. It was a Capcom anti-cheat driver that would disable a kernel mitigation, run the shellcode that you gave it, and then turn it back on. And then not too long after that, Bandai had an anti-cheat driver that did the same exact thing. And there's another CVE for ASRock RGB LED driver. Here's another one, and the list just goes on and on and on. So all of those drivers have flaws associated with them that can be exploited to elevate your privileges to kernel. And the fundamental problem here is that people write, this buggy code for reasons from way back from the earlier slides. VirtualBox has some bugs in it. It's a big software project. That's not too surprising. But then you have things like an RGB LED driver. It just kind of has really silly things like an ioctl that isn't protected at all, that allows you to just straight up say, hey, I want to read from this physical memory address, or hey, I want to write from this physical memory address. And then that driver gets signed by them and by Microsoft and published to the public. And there's no mechanism for revoking the signatures on these vulnerable drivers. So essentially, the bugs in these drivers become unfixable as long as you can find a vulnerable version of these drivers. Any one of those drivers, because they're signed, they're validly signed, you can take them on an up-to-date system and load them into the kernel, and then run an exploit against them, and then elevate your privileges to kernel. A lot of the time, exploits can be really complicated or really fragile, have problems with stability. But a lot of these drivers, they're not so much memory corruption bugs as they are just really bad implementations. And because of that, the exploits against them can be really stable or really guaranteed. And this code integrity options flag gives us a really easy way to kind of take an arbitrary read-write primitive from one of these drivers and turn it into code execution. And all we have to do is modify that one value. So we take our read-write primitive, we find the CI options flag, and we clear it. So it's 0 now, just like it was when we saw when it was disabled. Now we can load any driver we want into the kernel. And then now that we're running in kernel space, we don't even need to re-exploit in order to reset the options flag to on. We can just use the kernel code execution that we have from loading the driver to reset that flag, so that now the system is none the wiser of what actually just happened. And because all we're doing is clearing that flag and then loading a driver, we don't even have to worry about exploit mitigations like control flow guard or smap or nx or anything. It's almost like we're taking advantage of like the normal way that Windows expects you to get code loaded into the driver or the kernel. So the first step in building something like this is to actually locate that CI options flag in memory. Before in WinBag, we had the kernel debugger, we had symbols. So we could just directly dump the value of that this global by name. But in the real world, unless your exploit is going to download the symbol from Microsoft Symbol Server before running the exploit, you'll have to find it manually, as it's not an exported symbol from the DLL. So one way of doing that is to start at the initialize function that is an export from the DLL. And then we can see that towards like the end of this really short function, it calls a private initialize function and still passing that first argument, which if you remember was the kind of like the input options. And then the very first thing that this private function does is set, take that first argument that was passed to it, and then move that value into the global. And that's really all it does. So, and we confirmed that before, where we saw that the value of 6 that was initialized at the beginning of the function in NTOS kernel was the same value 6 that was in the global that we could examine with the kernel debugger at runtime. So following this set of pointers in the DLL on disk that you can just read, because you're an administrator, even any user will be able to read that file on disk, will give you the RVA of the options flag inside of the DLL's address space. But that doesn't give you the address in memory of it. You still need to find the base address of the code integrity DLL in order to fully find it. So luckily, Microsoft has a function that we can call from user space that will just tell us what that value is. The function is mostly undocumented, but it's still there, it still works, it's used in a lot of places. You can see that these structures are copied from process hacker source code. And the function is NT query system information. And this has a lot of like undocumented arguments to it, one of them being 11, or system module information option, kind of information. And what that does is it returns to you a list of the modules loaded in the kernel. And it gives you the full path name, it gives you the image base address. And the image base address in this case is what we're searching for. We want the loaded base image, or like the base address of the code integrity DLL in the kernel. And then we simply add the RVA that we got from looking at the DLL on disk, and now we have the full address in the kernel. So an example implementation of these steps can be found straight up on GitHub by Firefox. The project is called DSC Fix. And you can see here, running it on Windows 10 system. All you have to do is run the program. Right down in the middle there, it says that it finds the base address, and then it says it's going to modify the value at that address, and then it unloads the vulnerable driver, and then it exits. So DSC Fix doesn't load like a payload for you or anything. All it does is just set that code integrity options flag to 0. And then now you can use screate, scstart to load whatever drivers you want. However, there's a bit of a caveat on newer systems, and DSC Fix even warns you about this at the very top of the output. And it says that, warning, improved Patchguard version is present, and modification of data region will lead to delayed blue screen of death, which is obviously something we don't want. So let's look into that and see if we can get around it. So Patchguard, also known as kernel patch protection, along with driver signature enforcement, was first introduced in Windows Vista, and it's been improved upon a lot since then. And what it does is it watches, certain, special values in the kernel that are often taken advantage of by malicious actors in order to kind of maintain both security and kind of just stability or integrity of the kernel. For a long time, even antivirus vendors were going in and just throwing hooks all over the kernel, all over the place, in order to do their implementations of keeping watch and kind of guard over the system. And part of the problem with that is that those hooks might be making certain assumptions, and that can lead to instability in the system when those assumptions get invalidated, and the system will crash. And if you have for some reason 2 different antivirus systems installed in a computer, they're going to be trampling each other's hooks, and it's going to become a big mess. So for those reasons and others, I'm sure Patchguard was introduced to kind of take watch over like the kernel's certain data in the kernel, a lot of the code of NTOS kernel itself, and a whole bunch of other things, which from the kernel debugger, if we examine kind of the documentation for the bug check code that Patchguard throws when it blue screens the box, it gives you kind of this big long list of reasons why Patchguard might blue screen the box on you. As you can see, the list is pretty long, so it watches a lot of things, but it doesn't really give you any detail. Like for one of them, number 8, it says object type. It doesn't give you, what it's looking for, or like how frequently it's looking for it. The details on it are pretty sparse. But as DSC Fix kind of told us in more recent version, this wasn't always the case, but because Microsoft kind of caught on to people finding ways of clearing this value and then loading arbitrary code into the kernel. In an update to Patchguard, Microsoft actually has Patchguard watch the options flag now. So if Patchguard finds that you have changed this value from the default when the system was booted, it'll bug check the box on you. But the key part of that statement there is it'll do that if the change is detected. So like I said before, details on how Patchguard actually works can be pretty sparse. You can find many white papers out there now on kind of disabling or counteracting the different versions of Patchguard. as it's kind of evolved over the years since it was released. But the details on its implementation and how it functions are hard to find. A lot of the times, people have avoided publishing these details on purpose to kind of try and make it harder for attackers or to avoid helping attackers. But that said, it's generally understood to not perform its checks very frequently. You have to imagine that Patchguard is, watching, much of the kernel address space. It might take a while to go and check some or double check all of these values, which is going to take time or be a performance hog. And those are things that Microsoft doesn't want either. So you can even try it yourself, run DSC Fix on your up-to-date system, and then just see how long it takes for Windows to blue screen. It might take a couple seconds, or it might take a few hours. It really just depends. That said, in seconds or even milliseconds, you can disable driver signature enforcement, load your driver, and then re-enable driver signature enforcement. And now when Patchguard is checking that flag, there's only a very small window where that flag is not set the way that Patchguard expects. And you can avoid a blue screen most of the time that way, just by flipping it, loading a driver real quick, and then flipping it back. That said, the assigned driver exploits, some of them give you arbitrary memory read write. Some of them give you just straight up code exec, like the Capcom driver. They're not limited to just targeting the CI options flag. It is just arguably one of the easier things to do, because all you have to do is change one D word in memory, and then now you have code exec. But there are other techniques or other that you can use for exploiting these drivers that don't affect values that Patchguard cares about at all. An example implementation of that you can find on GitHub by the same author as DSC Fix, Firefox, is TDL, which is short for Turla driver loader. And it's based off of a technique that was used by the Turla malware. And this just writes I think it uses the same VirtualBox driver, and it uses one bug to write the shellcode into memory, and it uses another bug to just execute it. So it doesn't have to touch that options flag at all. And Patchguard is going to be none the wiser that there is now code running in the kernel. So these sorts of exploits, DSC was implemented in Vista. Attestation signing was added in Windows 10, however many years later that was. And Windows 10's been out since, about 6 years now almost. And this sort of technique, still works, today. There are a lot of vulnerable signed drivers out there. A lot of them provide you very stable exploits. And maybe it doesn't even take a lot of work to change your exploit from one driver to another. If you have this, a technique of building code exec out of an arbitrary read-write primitive that doesn't bother Patchguard, or maybe it does, but you take care of it quickly, and that small chance of Patchguard blue screen doesn't bother you, then any signed driver out there that you find that has a read-write primitive that you can build up on, it's not going to take a lot of effort to translate the rest of it, just kind of almost swap in the read-write primitive there, and then the rest of your exploit works exactly the same as it did before. And there hasn't really been much work towards a mitigation on this. Really, the only thing that we have on a lot of systems right now is antivirus signatures. So some of the more well-known signed drivers that have bugs in them, like the Capcom one that got a lot of attention for disabling a protection mechanism, running shellcode, and then re-enabling the protection mechanism. There's almost just like no excuse for that. Those will actually be flagged as malware by a lot of antivirus vendors now. However, their antivirus vendors don't flag on all of the known ones, just some of the more known and more known to be abused ones. And there are also probably a lot of signed drivers out there that have bugs that don't have CVEs associated with them. They're not publicly known. And obviously antivirus vendors aren't going to be flagging on any of those. So it doesn't really solve the core problem here. So how can this be addressed and by Microsoft or by IT at home? Like how can you prevent something like this? So I think that even though it's been a long time since Microsoft has kind of been addressing this issue, I think that the answer that they are coming up with is a big one, and I can see that it probably took a really, really long time to implement. And I think that their answer is virtualization-based security, or VBS for short. This was also introduced in Windows 10 1507 on enterprise editions. And the features have been making their way into all Windows 10 editions over time. I think that in Windows 10 20, like H1 or H2 specifically, most of the features are now ported over. Since it was first kind of released in its initial form all the way back in 1507, it's gone through a bunch of iterations, and kind of different names have been associated with it over time. And now, for finding more info about it, you can look for documents and articles related to device guard, core isolation, or memory integrity. And what VBS and it's kind of allows you to do is code integrity is now enforced by HyperV, the hypervisor. So really part of the issue with Patchguard and the kind of DSC options flag too was that they exist in the same kind of security context or address space as that they're trying to protect. So being able to take advantage of all of these signed driver exploits, to disable driver signature enforcement, or and then once you get running in the kernel, if you want to, do things that Patchguard might complain about and cause a blue screen for, there's nothing really stopping you from like a hardware or security mitigation perspective from, attacking Patchguard directly and turning off Patchguard, because it's running in that, the same context you are. You have just as much privileges as it does. But now with VBS, with the hypervisor, it's taking care of all of that, and it's one step kind of above or below. It's one step more privileged than the kernel itself. The kernel can't directly modify the hypervisor. And as we saw with the driver signature enforcement, all it did was prevent you from loading an unsigned driver when it was enabled. But now with this HyperV enforced code integrity, it gives Microsoft a lot more power. So similar to the user space ACG, or advanced code guard exploit mitigation that you can find in the security center, it will straight up block you from creating new unsigned executable pages. And it will also block you from modifying existing executable pages. So if you try to mark a executable page as writable, it will deny that. If you try to write to an executable page, it will deny that. So it's really not, with VBS, there's not really any way for you to create new code in the kernel that isn't signed and trusted and verified by the hypervisor. One kind of hurdle with VBS kind of being really widely established is that it has a lot of moving parts. So with driver signature enforcement, it kind of came with a kernel. People didn't really need to do anything to have it kind of turned on and protecting them. They just get Windows, and then they're protected. Driver developers had to do a little bit of effort to get their code signed, but from a user standpoint or from an IT standpoint, there wasn't really anything for you to do. But with VBS, there's a lot of moving parts. The processor needs to support virtualization and Hyper-V in general in order to be fully secure from tampering itself. Hyper-V and VBS require that you have secure boot and a TPM, like a physical hardware on your motherboard. And in addition, there is now new requirements on drivers for compatibility with VBS. It's not too hard to have compatibility with it. This link here gives you a big list of guidelines from Microsoft for ensuring that your driver is compatible with VBS. Short list here is opt-in to no execute. There's a whole bunch of APIs from the kernel that are now blacklisted, which sounds pretty bad, but it's really just APIs that are work around with maintaining memory. Before in the kernel, if you did like allocate pool, you could execute that memory if you wanted to, but now you need to use a kind of the NX versions of all of these APIs to avoid having these kind of executable pages being made and then being bug checked on by HyperV. And for historical reasons, the drivers have, when they're made, they have an init section in them that's marked RWX. That hasn't really been important for a while, but now with VBS, they are now requiring that that section and all the other sections in your driver be either write or executable and not both. But, and kind of to make sure that people start making valid drivers, Microsoft has made compatibility with VBS a requirement for drivers, going through their program since 1607. But despite that, here we are in 2021, and I can't turn on VBS because my HTC Vive Bluetooth driver is incompatible. And you can see that driver date is 2017, which is obviously after 1607. And even Microsoft's own drivers, in this case for a webcam, don't support VBS or memory integrity. And unfortunately, the answer to this thread was just to turn off memory integrity, which makes security people cringe. Turning off security mitigations or rules just to make like a webcam or something else work is very infrequently a good idea. So it's hurts to see that kind of like pushed as a potential solution to this problem rather than having Microsoft actually make the driver compatible. But that said, there is some really great progress being pushed forward. For example, just last year, Microsoft and VMware worked together to get VMware Workstation and HyperV working together at the same time. Previously, if you tried to have two hypervisors working running at the same time, it would not work. But now, good news for people who want to use Workstation for their virtualization, like either for development or testing or whatever. They may not be using HyperV for that same reason, but they can now turn on HyperV and take advantage of the security features that it provides, as well as keeping the development environment that they might have with VMware the same. So I see VBS as a huge step up from DSC. Not only does it give extra, kind of more general purpose protection against new code, being made in the kernel at all, regardless of kind of what the kernel wants to do. So like no longer can you, just turn off DSC and then load a driver. These new protections on modifying executable code and on modifying or in creating no executable code kind of protect the kernel much more generally than DSC did previously. And because of that, and because VBS is still relatively new, it's not really percolated much, or percolated many places, not really enabled a lot of places. Bypasses for it and research on how it works or how you might bypass it are still kind of evolving. Right now, the information that you can find online is really just about Hyper-V exploits directly, which is clearly a much bigger hurdle for attackers than finding some random RGB LED driver that was poorly implemented. And the other option is hardware attacks. You can find info about those online, and those are obviously infeasible for an attacker at a lot of scenarios that they might be interested in using. So that is all I have. Are there any questions?
Yeah, it seems like we have a bunch. So first question from Matt. Why do you think Microsoft doesn't have a certificate revocation process for kernel drivers?
Honestly, I have no idea. That was kind of like the first thing that came into my head when I learned about these like DSC bypasses. Um, I imagine that it might be for compatibility reasons. Microsoft has historically made a lot of decisions regarding compatibility and trying to make sure that things are backwards compatible with different versions of Windows. Um, that could be why. That said, Apple has taken a kind of stance for this. They actually have a module blacklist um, that they maintain and they actually add to. So Apple has taken the stance of adding a blacklist into their system for kernel extensions that run in the kernel. Don't know why that Microsoft hasn't.
Thank you. Yeah, that's kind of interesting why they haven't taken that approach. And leading into our next question, Sarah was wondering, how prevalent is this attack surface, especially given its implications with privilege escalation to the kernel?
I'm not sure if I'm understanding the question specifically, so I'm going to answer it in the way I think that I'm understanding it. And it's that, that big pile of CVEs that I showed in my slide deck wasn't even, all of them. There are lots more CVEs that are listed and lots more drivers that might be vulnerable. And all you have to do is carry them with your malware and then drop it, load it, exploit it, and then you're good to go. So there is a lot of area or a lot of potential for this sort of attack to be to make work. Is there any? I don't know if she can speak or answer in the chat if there are more clarification for the question.
She could put it in the chat if she needs more clarification, but yeah, that I really do see your answer, because I mean it definitely is prevalent. I mean, even like you said, there aren't even CVEs for some of them, and most recently the one by Google was pretty bad with the ODE they submitted, where there was also a sandbox escape. So it's clearly a problem. And that kind of leads us into our next question from Mark. How receptive is Windows to disclosures on its drivers kernel vulnerability?
I don't really know the answer to that. I've never been through kind of the process for submitting a vulnerability to Microsoft. I think for like these drivers itself, these aren't made, a lot of these aren't made by Microsoft. They're made by, vendors of RGB LEDs or, VirtualBox, just a lot of entities that are outside of Microsoft itself. So I would imagine they wouldn't even take reports on, problems like this, and they would direct you to report them directly to the people that actually develop the driver that has the issue itself. That said, if there's a vulnerability in the Microsoft's kernel itself, then obviously they'll be interested in hearing about that.
Yeah, thank you. And so we have another question. In your talk, you mentioned VBS is making their way into all Windows 10 editions. What can consumers do to ensure they have VBS?
Yeah, so I would definitely recommend you look into seeing if your system supports it. A lot of kind of like laptops or like Surface stuff support it out of the box, but it might not have been enabled by the manufacturer. You might have to Google specifically for your motherboard or laptop model for turning on some options in the BIOS, specifically either making sure that you have a TPM or trusted platform module in there, or if you have a newer Intel CPU, they have like there's like an option that you can turn on to use like a TPM that's on the CPU itself, and that you might have available. If you have like a desktop computer that you're comfortable with like opening up and adding parts in, you can go on Amazon and buy a TPM for like $15 and install it on your motherboard if you have the header for it. And then simply go check if you have secure boot enabled, make sure it's on, and then go to the Windows security settings in Windows 10 itself, and then just go and turn on core isolation and memory integrity, and then you'll be good to go.
Yeah, thank you. And in regards to the previous question, it seemed like you answered. She put in the chat that you answered it, and she apologized for any awkward wording.
No problem. Thank you.
And to anyone who's currently competing in the CTF right now, there is a conference flag in the chat. So thank you for attending, and there are some points there. Also, if you didn't notice, Janet put in the chat, thanks for attending, and she put a link for Lockheed Martin's system. And so you'll be able to get other notifications from them on future events and so on. And so that's definitely a great opportunity. So go ahead and click that link.
Cool. And I will be available for both of the networking sessions later to answer any more questions about the talk or stuff in general. And also, if you guys are interested in jobs at Lockheed, I'll be there at the networking session to talk about those two. Both internship and full-time positions are available.
Yeah, that's great. Definitely come out to those. It's a great opportunity to meet some of the speakers and other security professionals who are joining us today. And with that, before we close up, Branden, do you have any final thoughts to leave us with?
No, that's all. Thank you very much, everyone.
All right, thank you for coming, everyone. And thank you, Branden, for your great talk.